Hello, folks, and welcome to Rational Science, the only site on the internet that does physics rationally.
Well, does physics, so you
Does
stop
physics.
there. Full stop.
Okay, we're going to have a special day today because I don't always find my son. I never know where he's at. Okay, so today I found him. And so because of that, we're going to do something we wanted to do for quite a long time, and that's have him ask questions out of the blue because I don't know what he's going to ask, and I got to answer them. And they're related mostly with the rope model of light and gravity. Okay.
I mean, if we get there, you said you had a bunch of things you have to answer first.
There were several questions. I'm going to go through the questions that people asked first. Okay. And then we're going to move on to to those questions. And of course, people are welcome to ask questions. Okay. And we're going to try to answer those as well. They can be on any topic, really. Okay. And I hope we are still online. I hope we are.
Yeah, I heard it.
Yeah. You're hearing. Okay.
Yeah, twirl my beard a bit. I look like a villain.
Okay, so let's go with the first question or comment that people made. It's related. I'm going to do the first extinction. There's like 4 questions there, so let me address those first. Says whether from infections or immune activation in the womb, chemicals and electromagnetic stressors, or a neuroinflammatory profile other than in the case of blah blah blah, no hard genetic cause has been found. Yeah, a lot of people believe that autism is related to chemical activity and not to what we propose here, and that is that it's got at least something to do, or quite a bit to do, with the fact that we've lost genetic diversity. That's my argument, okay? And people question that, especially people who go against vaccines, who believe that the corporations are poisoning us with a lot of chemicals that they put in the food and things of that nature. Okay, and another fellow along the same lines, he says, lack of genetic diversity never prevented rabbits, cats, or camels from overtaking the country. The mouse experiment also blamed population density, so what explains mass homosexuality and autism in rural Australia? Okay, I think the problem is chemical. Again, all these people believe that it's chemistry, right? It comes from polluted food or polluted medicines. Okay, so yeah, lots of people today, especially those who are a little wary about the government intervening in their lives. They believe there is this conspiracy. I guess it is a conspiracy theory in a sense. There is some truth to it. I'm not going to say that it doesn't affect us at all, but I don't think that's the primary mover for why we're having some of these, we could say, mental problems, and we put them all together. Okay? Personally, I think a lot of that has to do primarily with genetic diversity. We lost it, and secondary, maybe density has something to do with it. We're all in the cities. We're all cramped in there more or less, and we don't know who our neighbor is anymore, even though he lives next door, in an apartment. And so I think that's got some effect on people, the educational system. Okay, a little bit of that, but if I had to weigh it on the scale, I would say that 80% of it at least has to do with genetic diversity. And part of that, the reason I think that way, is because of Calhoun's experiments showed that after 2 years that the mice were multiplying. Okay, for those of you who know what happened there, they came first from the same stock. Okay, we have the founder's effect there. And that's followed by the fact that, they had density. After a while you had 1,000 mice, and after a little while you had 2,000 mice, always in the same space. And so I think those are the primary factors. And I think that's what's happening to humans as well, which was, by the way, the conclusion of Calhoun, okay, that they went berserk, all these mice, because of density. He didn't even I don't think he considered founder's effect. Maybe he did, I don't know, but I would say that's probably the primary cause. And here we have another fellow along the same lines. I'm really getting tired of your religion of clones. There's more difference between me and my fellow man than there is between all the dogs, wolves, and coyotes in the world. I think that's not true. Okay, I think he's got his data wrong. I think dogs, wolves, and coyotes are different species. We are the same species, different races. And so I don't think what he's saying there is not true. I don't think that's a fact, okay? And he says, we are a diverse, huge species cluster, and we are certainly aren't having any inbreeding troubles. I'm going to dispute that. Here we have a case of the chimps, okay? Some news from the past, 2012, chimpanzee populations living in relatively close proximity are substantially more different genetically than humans living on different continents. They had like 100 chimps, and they had more genetic diversity than the entire human race. And so I think that's the first bit of data, right? Take it for what you want. And here's another, okay? Oh, on the other side. And here's the other one. Let's see if we can get this up here. These are the couple cases. One is Charles II of Spain, known as El Hechizado, the Bewitched. And he was from the Habsburg family, which did a lot of inbreeding for a couple generations. By the time you get to the 1700s, he had mental problems. And then you have the Romanovs. They came all from Queen Victoria, and they also inbred. And by the time Alexei came up in the early 1900s, he had hemophilia. In fact, it was said that that's the disease of the kings, of the czars, right? And the Amish are having all kinds of problems, genetic problems of different nature. In fact, some rare genetic diseases because of 350 years of inbreeding. They came all from the same stock, so it's a great experiment, really, in which they all inbred for 300 years, and from like a stock of maybe anywhere between 1,500 to 2,000 people, we have 350,000 Amish today. And after 300 years, you would expect of inbreeding, you would expect to see some problems. And there you can see what's happened with humans. Okay, if we go with the earliest human-like creature, which would be Ehud, right, 300,000 years ago, to today, I think we had a lot of inbreeding. We all come from that stock. Some Adam and Eve, not literally true, but we can trace our lineage to about 300,000 years ago. And I think that we've been inbreeding for quite a while, and now we're starting to see some of the problems, especially because we have density. Okay, that means that we are all in the same city. Okay, you maybe have the girl next door, the girl across the street. That's the one you marry, or you marry someone in your town or within your race, and I think that all contributes to our loss of genetic diversity. Anyways, that's my take on that briefly, right? And then the last one here, a fellow says, please make a video on your opinion of Danny Vendramini, Neanderthal predation theory. I have talked about Vendramini in the past. I didn't make an entire video on him, but here's a summary that came out of the book he's selling out there. And he says, the evolution of modern humans is the result of systematic long-term sexual predation and cannibalism by Eurasian Neanderthals. We turn to complex social societies to fight them off. Okay, I got a couple problems with what Vendramini is saying. The first one, I'm going to have a problem with his version of Neanderthal there. You can see looks a little monstery. He's a little monster. Look at the face. And I think this is a little Hollywood-esque. I would go more with the one Boulet drew in 1909, which was the original notion that we had of Neanderthal. And I think I would prefer any of those anyways to the one in 2015 where the guy is, it's that white guy there. And I think if a girl had to choose, I think of all three of them, she would sleep with the guy on the right, not with any of the other two. And yeah, if you make the one on the right, if you make Neanderthals more, desirable to women, then we can all imagine, yeah, we did sleep with the Neanderthals, and that's how they disappeared. So what they're trying to sell you is the extinction theory based on intermarriage with the Neanderthals. And of course, if you put the other two fellows there, then very few people will believe it. But the question is, what did Neanderthal look like? I think it's important. And I would say that Neanderthal was the woolly man. He looked like that guy on the left first. And I think if it were me, I would put more hair on him. This fellow lived in very cold climates. He lived in Europe. At the time, Europe had glaciers that extended way down south. So this guy was a snowman. He was a Yeti, abominable snowman, So, and I would think he was hairy. So I don't think that guy in white, I don't think that's the guy that looked like Neanderthals at all. Yeah, so I think all they're trying to, well, I put the diaper in there, but because, it's so ridiculous for them to put such a white guy, just hair in his chest, looking good, Mm-hmm. The girls would say, well, I would sleep with that guy, Yeah, no kidding. That's why they can sell the interbreeding theory. But that's only because
if they put a monkey,
that's the point.
Doesn't sell as well.
And that's the point. Okay, getting into the physics stuff. Here we have a fellow says the following. He says, wait a minute here. How come I can't see that?
Oh, it's got the little eye.
Huh?
Touch out. Yeah.
Oh, is that what it is? Oh, okay. Okay, so here it is. One fellow says, none of them are dimensions, they are number line. No, that's what I said, I'm sorry. And he said, many misunderstandings here. It's clear from that statement you don't understand what a dimension even is. Okay, I don't know what a dimension is. Number lines are dimensions. States of being are dimensions. Any descriptive term is a dimension. At least could be. And these are what dimensions are, or what a dimension is. Okay, so this fellow says a dimension's everything. Dimensions are anything you can think of. They just put them in there and say anything you can think of, at least any descriptive term is a dimension. State of being.
Color could be a dimension.
Yeah, everything. Even God is a dimension. So the problem here is, again, people don't define their terms, and then they tell me that I don't know what dimension is. Okay, so let's educate this fellow. Okay, let's find out what he doesn't know. Okay, here's the first one. Here's the definition of dimension. This is from the official literature out there. One is from the Wikipedia, the other one is from Wolfram. They both basically say the same thing. First thing is they clarify that dimension is of a mathematical space, whatever that is, or object, and the other one says dimension of an object. So we're more or less on the same, in the same ballpark here. And then it says, the first one says, is informally defined as the minimum number of coordinates needed to specify any point within it. And the other one says something similar, says, is a topological measure of the size of its covering properties. Roughly speaking, it is the number of coordinates needed to specify a point on an object. So they're both saying the same thing. It's the number of numbers, because that's what a coordinate is. Here we see what the definition of coordinate is, more or less. Let me get this up here. And a coordinate system is a system that uses one or more numbers or coordinates. So what is a coordinate? It's a number. To uniquely determine the position of the point or other geometric element on a manifold such as Euclidean space. So what do they say? They say it's the same thing. It's the number of numbers needed to specify a point. That's essentially what a coordinate and a dimension is. They're synonyms. There's no difference between the word coordinate and the word dimension according to these people. And there you see the Wolfram says a set of variables which fix a geometric object if the coordinates are distances measured along perpendicular axes, right? And they're talking about distance traveled, meaning what? Number lines. They are known as Cartesian number lines, but they call them coordinates.
Dimensions equal number lines?
Yeah, essentially, not really. I'm going to specify that right now, clarify that right now. And so what is a coordinate? What is a dimension? Number of numbers. That's all needed to specify a point in Euclidean space. That's more or less what it is.
On a grid.
Yeah, on a grid or whatever. And so here we have what it really is. I mean, for the purposes of physics, we're doing physics here, right? We don't care about math, okay? So here we're doing physics. And here you see the differences between physics and math. The ones on the top, physics. The ones on the bottom, the one on the bottom, math, okay? Dimension, length, width, and height, okay? That's it. 3 dimensions. You want 2 of them, length and height, length and width, no problem. Width and height, we'll go with that. But what do they talk about? They talk about, or what do they refer to? Orientation of an object. How it looks, from given how it faces, in other words. Coordinate has to do with locations, and you can see the arrows point in the opposite direction. They point towards the object. You have, for example, a room, and you're going to locate that object within the room with these so-called coordinates, right, that we use in physics. And what are they? Longitude, altitude, and latitude. And then vectors. What are vectors? They're direction of motion. We have motion there, and again, it's outwards. It's the 3 mutually perpendicular directions that an object can move in. And there you have depth, breadth, and elevation. None of those are quantitative. They're only qualitative. They have only 2 properties, and that's direction and perpendicularity, orthogonality. What does math use? Does math have any use for these qualitative notions? Absolutely not. What math uses is number lines, and all they have is magnitude and direction. The problem with direction is that direction is a qualitative concept. Math has no use for qualitative concepts. And so really all they have is this thing they call number line, and they call them dimensions. Sometimes they call them coordinates, and they call them vectors. It's all the same thing to mathematicians. So all I can tell you is that, math does not use dimensions at all, or coordinates for that matter. They use number lines. Everything in math has to do with numbers, only numbers. So they use the word dimensions, and they call them length, width, and height, and then immediately they put some number in there talking about how much, how long, how far, that sort of thing, how much time. So that's how all these number lines have become dimensions and coordinates. Okay, next issue. So we move along here. Paul says, if I drop my computer causing damage, do you think mathematical descriptions damage the computer, or do you think forces did the damage? And he says the same thing for the other one. Says, or do you think field did the damage? And the same thing for computer. He says, do you think energy did the damage? And so he's talking about forces, fields, and energies, and he says they are physical. Physical? What do you mean physical? What does physical mean? And of course they don't define physical ever, so they can use these words. They can say forces, fields, and energies are X. And as long as they don't define X, you don't know what they said. That's the issue. Okay, and it says, far from being conceptual, only residing in the mind or minds of humans as abstract ideas. So that's what he thinks are concepts, right? Concepts is just what resides in the mind. Okay, yeah. If you define a concept that way, then you can get away with anything, because that's not a good definition. What do you mean reside in the mind? Does a tree fit in your brain? Is that what it is? That's how it resides in there, So you got to define really what a concept is, and that's not a rational definition. Certainly it's the one he just copied out of a book, a dictionary or whatever, and he calls it, this is the definition of concept. Even to this day, philosophers, like at the Stanford Encyclopedia of Philosophy, are debating what the hell is a concept. Okay? And we have a problem, because here you have these are definitions that you find there. Here's the one for force. Okay, strength or energy as an attribute or action of movement. That's out of Oxford Dictionary. Force and influence. That's what it is. Influence. I guess influenza. When you get the flu, that's a force that can cause an object to change its velocity. Okay, so that's what force is. What is field? Field, a physical quantity. So we're talking about a quantity. Okay, so that's what a field is. He says it's physical. Can we say that a quantity is physical? And it says represented by a number. Okay, so yeah, a field is always a bunch of numbers. That's all it is. And what is it that has a value for each point in space and time? So all they're saying is you look at the strength of the field. That's essentially what they look at, and they put numbers in units that extend ever weaker from the farther they get from ground zero. Okay, and so that's a field. If you take all those numbers put together, that's a field. So it's a bunch of numbers. Field, the influence. That's according to dictionary.com. The influence. It's an influence. That's what a field is. Of some agent, whatever agent. It's like the agent doesn't count, or that field is not an agent. It's just the influence of the agent, right? As electricity or gravitation. Considered as existing at all points in space, right? Because it's just a bunch of numbers. They just talk about the strength of the field, not the field itself. Field is the whole thing. It's a bunch of strengths, you could say, a bunch of numbers with units, and defined by the force it would exert on an object placed at any point in space. And then what do we have? We have energy. What is energy? Well, here we have it. Our good friend Richard Feynman, Nobel Prize, right? He told us what it is. It is important to realize that in physics today we have no knowledge of what energy is. Had no clue whatsoever.
Well, it's vaguely defined.
Well,
so
yeah,
obviously
right. Right. Well, you can see how it's defined. Energy, the capacity. And then you look at it, elsewhere it says energy, the quantitative property. So no, these things are not physical, as this fellow suggests. And absolutely not. They're not, we don't have any physicality to these concepts. These are concepts, and concepts are not what is in the mind. Concept is simply a relation between two objects, okay? And who performs it? A human. Without humans, we have no concepts really out there. We created all the concepts. Mother Nature did all the objects. We did concepts. Yeah. Okay, that's the way it works. Okay, another fellow along the same line talks about field. What is a field? Well, a field is a movie, he says. Yeah, agreed. It is a perturbation.
Perturbation. Whoa, that's a nice word.
Oh, yeah. I'd like to insult you. You're a perturbation. Force is not energy. It is the opposite of energy. It is the loss of energy. Okay? Ether is not a movie, though. It is non-Cartesian, and he says it's pure potential. Ooh. Okay, so ether is just pure potential. So he's saying
you know why it's pure potential? Because whatever you need, he pulls it out of the potential bag.
Yeah.
Ether isn't until whatever you need, then you need dark energy? Ether made the dark energy. What else do you need?
Yeah, but even in that case, ether is misconstrued.
Oh yeah?
Yeah, because ether is not just energy or movie or not a non-movie or potential, whatever you want to call it. Ether was a medium, right? That was always in motion. It was ether means air.
Wait,
Greek air.
A medium that's in motion?
Yeah, that's here it is. In fact, we have it illustrated for you, so you don't have to break your heads.
It's not a fart, is it?
There it is.
Or is it a fart?
Yeah, there you have it. That's what the ether is. A bunch of particles that was out there, and the movement of that was after Robert Hooke came up with the wave notion of light. After that, the ether light was simply the undulation of the ether. And what was it? A bunch of particles that are moving up and down. That's what it was all the way to the end of the 19th century when relativity and quantum mechanics overthrew the ether, supposedly. All they did was really change the name, because we still have the false vacuum in quantum mechanics, and we have in relativity what is known as space-time. What is space-time? A point at each, an event that happens at each point in space-time. That's what space-time is. And there you have it, each point in space-time. And what they do, they move around. When they move up and down, you have what is known as light, wave nature of light. Okay? So that's essentially what it's always been, a bunch of particles. That's all that ether was ever since the days of the Greeks. Nothing has ever changed. And all those people say, Bill, you don't know what the ether is. Well, but you never tell me what it is. Don't tell me what it ain't. Okay? I want you to tell me what it is. And if it's if it's a what, if it's a thing, point to it. Give me a picture of it. And if it's a concept, define it. Very simple. You either define or you draw. and they never do either one. They say, well, you don't know what it is. Yeah, I know. I'm ignorant, as you're going to show me today, right?
Nope. I'm here to ask him hard questions.
Oh, Jesus. Okay, you'll see. I'll get you. No plate of soup for you today. Okay, here we have another fella along the same line. Let's replace space with the black sky. This guy's going to talk about the ether also. In the black sky, there are many bright dots that we call stars or planets. Okay, the black sky, instead of being empty, is full. It is an object. So the black sky, space, he's saying is an object, a thing. Okay, if it is, draw it. That's what I say, and tell me what gives it shape. What's the background, right? Elaborating on Bill's hypothesis, threads and ropes, the black sky is all that mass of threads and ropes that are not structured like an atom. So he's saying you have the atoms, right? That's what we call matter. And we have the rope, which everybody calls energy, the vibration of the ropes, frequency times wavelength, right? And he's saying that these ropes, they form this backdrop, right? And he says it's the ether, okay? The word ether, the medium that connects all objects, is an object and not nothing. Okay, so he's saying that ether is an object because ether is all those ropes. Maybe he includes the atom, maybe he doesn't, but I think that's irrelevant. But at least the ropes are included, right? And saying all the ropes, that's the same thing as space, and that's the same thing as ether. It's all one shebang, same thing. And yeah, we have a little problem with what he's saying because here you can see a little picture that synthesizes the problem. Here you have a bunch of ropes going in every direction, right? And the question is, what's the black stuff that gives shape to the rope? If the ropes, all the ropes together, just the ropes, right? That's the ether and that's space. And so what's the black stuff that gives shape to each individual rope? That's what he's got to identify, the black stuff. And he can't say the black stuff is space because he's saying that the ropes are space. That space, ropes, and ether are all the same thing. One and the same. He's saying that the ropes cover every little bit of space, and that's what the ether is. Okay, so that's his argument. And we're saying no, because you have to have two things here. You have to have the black stuff that gives background to the green stuff, which are the ropes. So you got to identify what the black stuff is in this case. And I don't think he would understand anyways, what the issues are here. So all I can do is just throw that out there for him to answer the question. Okay, moving on here, we have another fellow also talking about the ether, and he says about
ether.
Ether is not space. Okay, we have one that says it is space. This one says it's not space. Okay, space is ether's shadow.
What? What?
So it's so when we have the vibration of the ether, the wave, okay, the electromagnetic wave. He's saying that's a shadow that's moving. Okay, it's a shadow. Okay, and I guess you have light casting on this ether thingy. It creates on ether and gives you the shadow, which is space. The space is what's the shadow. Okay. So what's the ether then, right? And ether cannot be pointed to because it has no Cartesian. I don't know what that means because if you should be able to point to it if the ether casts a shadow, which is space, right? So if space is the shadow of ether, ether had better be a thing like a tree, then you can cast a shadow. Otherwise, you can't have a concept that casts a shadow. And he says ether is not a concept, nor is it an object. Okay, so he killed me. I don't know.
He has a third category.
Well, he's got to identify what category it falls under. Okay, all concepts and objects are either perturbed.
I mean, you either have shape or you don't.
Yeah,
the
but
third one.
Yeah, but that's
kind of maybe have shape when you need it, but not having shape when you don't.
It's what these people never define their terms. That's why they get away. They murder.
The whole point is they specifically don't define it so that they can get away with murder.
But they don't realize how important it is to define words. They think that's word salad and semantics and grammar. And he says, I came here to do physics, not to do semantics, Okay, another fella talking about plasma. Okay, here we have the plasma. Is the fourth state of matter. The famous state of matter. Electrons in a solid, liquid, or gaseous sample of matter stay with the same atomic nucleus. Okay? And what happens when you excite them? Heating a gas will form a plasma. Why? Because electrons are ripped away from the atoms forming an ionized gas. So what is ionized gas? It means that you're going to strip an electron away from them through some process. That means the plasma, which is a bunch of ionized atoms, right? Means that they're excited somehow by something. We don't care about that at this point. We just care to what is the plasma? And the plasma is an ongoing process. It never stands still. So you can't take a picture of plasma and say, oh, I took a picture of plasma. No, you did not take a picture of plasma. Okay, once you take a picture, that's not plasma because the word plasma means something in motion. And what I'm staring at is not in motion. Okay, so we got a problem with a picture that you took of the plasma ball saying, hey, that's plasma inside there. No, that's not plasma because plasma is always in motion. Plasma is a movie. It's never a photograph. Okay, that's the way the word plasma is defined. And it takes 100 years for these people to understand that. Plasma is a form of matter in which electrons migrate. Yeah, they're constantly migrate around the nuclei of the atoms. So plasma is always in motion. If you take a picture of plasma, that picture is not a plasma. You can't call that plasma because plasma is always in motion. You're reading more into the picture than what is there. Okay? The word plasma is a running boy, not a boy. Okay? Word plasma means flying eagle, not eagle. Okay? So if I take a picture of a flying eagle, what I have in the picture is an eagle, not a flying eagle. I'm putting more into the picture than what is there. All I have there is eagle, not flying eagle. And swimming fish, should I go through all the animals maybe? You know, a fish, if I take a picture of a swimming fish, would I see a fish in the ocean or in the river or whatever, right, in the water? I don't see swimming. Swimming, if I want to take a picture of swimming, I need a movie. I can't take a picture of swimming. And you can't take a picture of ionizing. If the gas is ionizing, constantly ionizing, I'm not taking a picture of ionizing. I'm taking a picture of the atom, or an atom that has a little ball next to it, which is the electron little bead there. But I'm not taking a picture of plasma. I'm taking a picture of I can't take a picture of ionizing. Okay, that's the point. Okay, and these people have a hard time understanding that. So here, let's go with the state first. Okay, here we have plasma is not a state of matter. Move this over here.
Hey,
cover your face.
I want to talk.
Oh, okay.
So as we can see here.
So plasma is not a state of matter. Why? State is a static concept. And plasma is the one on the bottom, ionizing. So you can't take a picture of ionizing. Okay? Can't be a state of matter.
What about taking a picture of ionized in the past tense?
Yeah, again, if any picture I take, I'll have a static image. I'll have, no motion. And the word ionizing and the word plasma both are running.
Well, hold on. Let me stop you there.
Yeah.
There's a difference between burning and burnt. A burnt kangaroo isn't a kangaroo. It's a burnt kangaroo.
Yeah, there's no such thing as an adjective in physics.
Yeah, I got you. But what would you call the chunk of just burnt meat? It's not burnt meat. What would you call it?
No, but I mean, first you have to identify the object. You can say, that's a kangaroo. Now, if it's burnt, now you're going to talk about something else.
The burnt kangaroo, what would you call it if it's not a burnt kangaroo?
No, I'm saying that there's no object called burnt kangaroo.
What would you call it then? After
you point to the kangaroo, you can say the kangaroo is burnt.
No.
And the fish will be swimming.
It's not a kangaroo anymore. So you can't call it a kangaroo.
You call it a bunch of carbon.
But it's not carbon yet.
I don't know. Whatever you have there. Well, I don't know.
Wouldn't it be easier to call it a burnt kangaroo?
Yeah, but you can call it a burnt kangaroo. What I'm saying is there's no object called a burnt kangaroo. Okay, there's no object called burnt. That's the point.
Yeah.
You don't look at the noun. You look at the adjective or the adverb and say, can I put an adjective, a verb turned adjective?
Well, by that case, right? I guess by the same token, you could add an infinite amount of adjectives of where an object has been. Because you could say the object that was down the street 2 minutes ago. You could add a bunch of qualifiers that are almost irrelevant to what the object is now.
Yeah, and for
whether
that,
it got burnt, whether it got moved, whether it got dropped.
But then what you're doing is comparing. because
Yeah.
burnt means that it wasn't burnt before. It's like dead and alive. You say, well, that's a dead cat, like Schrodinger's dead cat, but that means that you're comparing that against alive.
Okay.
You're making a comparison, but you cannot take a picture of the comparison of the concept known as burnt or dead or alive or whatever. You can take a picture of cat and then describe it and say the cat is burnt or whatever, dead or whatever. But my point is, there's no when you put an adjective and you say I can take a picture of a dead cat. No, you cannot. Not in physics. You can take a picture of cat, but not of dead.
But hold on.
Dead is
okay.
You're putting more into the picture than what is there.
Okay, then one more question to that. There are certain atomic elements that are man-made. Right?
Yeah. Uranium.
Well, not uranium. That comes naturally.
Well,
but the weird ones like Einsteinium.
Yeah.
Right? So those are man-made. So we got Lawrencium.
Yeah.
But you wouldn't call Lawrencium because it's, you'd almost say it's a process because it's only there for a fraction of a second. So when you point at it, are you calling it what it is now or how it came to be?
Well, the point here is, again, if it appears in our world, in the physical world,
you can point to it and look at it.
Okay, for gazillions of a second,
in that gazillionth of a second,
and you took a picture. You took a picture. Yeah. Let's say you were able to take a picture. Okay. The area of Lawrencium in front of you, right?
Isn't that like ionized gas? Because there was a process to get to it, like burning a kangaroo, but it is in front of you as it is.
Yeah, but the object that's in front of you is a bunch of, in this case, under the rope model at least, you have all these balloons.
Yeah, it's a very compact.
So yeah, you have this
ball of whatever,
multiple balloons.
It's a weird mass.
Right. It's got all the. You can take a picture of that and say that's Lawrencium. And you can take a picture of, I don't know, uranium and say, look, see how different they are, and say this is Lawrencium, this is uranium, even though they, they're radioactive and they immediately.
But then why can't you have a picture of gas and ionized gas? Look how different they are.
No, because now we're talking about something else. Because again, in Lawrencium, you're taking a picture of the atom, complex atom, a bunch of balloons. I can put a bunch of balloons together and say, look, this is what Lawrencium looks like. And I take a picture of just a bunch of balloons, right? One inside the other, or tied, clown balloons, right? So I build this model and say, that's Lawrencium. Okay, so I've got my model and I can take a picture of it. Nothing's happening in the word Lawrencium.
Well, kind of, because
it's not.
It's about to explode.
We don't care how it got there or whether the next second it disappears or breaks up or whatever. Okay. All we're saying is at a certain moment we have this Lawrencium thing. We took a picture, and here's the picture of what Lawrencium is or what it looks like or whatever. But you can't do that with plasma or ionized, because you're not talking about what is being plasma or what is being ionized. You're talking about the process. There, the word plasma includes motion. The word ionized includes motion. Ionized, when you put it in front of gas, it's an adjective, but it was a verb that was turned into an adjective. Ionization means you're pulling an electron out, right? So
I kind of get it. So it's very.
The question, people think we're taking a picture of plasma. Yeah. No, you're taking a picture or trying to take a picture of ionized.
I guess ionizing. It's not so much like Lawrencium. It's really more like fire, where you think of fire, and if you take a snapshot of fire and zoom in, you can't really see the fire.
That's why fire is not a physical object.
You just see the atoms.
Fire is a process of combustion.
It's weird.
And so you can say, so we should use the word fire or plasma, because when you say plasma, say, well, plasma is a noun. No, not in physics. In physics, it's not a noun.
But it's weird because
fire is not a noun either.
Well, it is and it ain't. The reason why it is because, well, yeah, obviously fire is just like the breaking of light that gives it shape, but it isn't really something that has shape.
No, but it's not the issue of shape. It's that the word fire,
it's
right?
A verb.
We should replace it by what it means,
burning.
Which is combustion.
Or burning.
Burning oxygen or whatever. So you've got a verb, and you're trying to take a picture of the verb, not of the atom. Okay? Because if I put an oxygen atom there, and you say, well, that's an oxygen atom. No problem, an atom, right? You can take a picture of an atom, but you cannot take a picture of combustion. Okay? Combustion is a process. And so you need a movie for that. You can't take a picture of combustion. That's what people don't understand when they say fire or when they say plasma. That's weird. The issue.
Yeah.
So language is absolutely important.
But it's tricky to define those because it's a concept. Fire is a concept.
Yeah,
because you
it
need
is
a
a
movie.
concept,
Because
right.
you need a movie.
Yeah, you need a movie.
That's-
Here you see it. In fact, where was there you see it. See, it's moving around. So yeah,
It's
so you can't
weird,
have it
though.
as a state.
I feel like there's still something there, but I'd have to really
Okay.
dig deep into it to get a good question. I need a question that'll really stump you. But I don't
Here you
know.
have plasma on the left-hand side. We all understand plasma because you're watching a movie, but you cannot take a picture of plasma because all I see there, I don't see ion. I don't see ionizing.
I get
What
it.
I see as atom is, if anything, I see electrons, but I don't see ionizing. For ionizing, you need the left one.
Yeah. There's still something there, but I can't get it yet.
Next
Something still nags me, but I can't put my finger on it.
Okay, next movie, next
Yeah.
week.
Next week I'll get you, but not this.
Okay.
You win this time.
Okay, a couple more.
Yeah.
Okay, and then we go into the questions. Okay, here's the first one. Newton actually just proposed an inverse square relationship, a proportion, not an exact equation. This came after Newton. Absolutely right. Newton had no equations in Principia. Okay, he had no equations in there. All he did was have qualitative explanations. In that sense, he was more of a physicist than what you have today, because even though he knew quite a bit of math, okay, he was very interested in math in that sense. He was interested in how this universe works, and he was at least honest and says, "Fingo non hypothesis." He says, "I have no clue." That's what he said in Latin. He said he didn't know how gravity works, and he said it was just so strange that he would not be able to explain how gravity works from a distance without a mediator. And he could not explain that, but at least he was on the right track. Okay, but all he did in his book, he was explaining qualitatively that looks like this gravity thingy. It has to do with masses and the square of the distance, the inverse square of the distance. Okay, so that's all. He other than that, he said nothing more.
We have someone ask. Ans, tell Bill to pause the GIF and ask him what it is, the plasma. But you already did that, didn't you?
What the plasma is?
If you pause the GIF, ask them what it is.
Yeah. What it is, we call it plasma because we use one word for it, but we cannot take a picture of ionizing. I want you to focus on that.
That's essentially what you did. You had the frame.
Yeah,
right
I take
next
the
to
frame
it.
there, and what you have is in that picture. What you have is atom. We're going to go with a quantum version. We have the atom and an electron, right? That's what we have, and they're separated. They're not close together, they're separate. That's what we're staring at. So far, we see no motion. We don't know what's happening. We don't know that the atom lost that electron. We don't know any about that. We don't have that information in a single picture, in a single frame. We are reading more into the picture than what is there. Again, I like to use the case of the flying eagle or the swimming fish because when I take a picture of a swimming fish or a flying eagle, I'm not taking a picture of flying, I'm taking a picture of eagle. And when someone says, "Oh, that's a flying eagle," no, that's not a flying, that's an eagle. I can't take a picture of flying.
Yeah.
Flying, I need at least two. Then I can compare them and say, "Oh, this guy was here and then now it's over here." That's flying.
Yeah.
But in one picture, I cannot synthesize flying. You're reading more into the picture than what is there. Same thing with plasma. Plasma, you have the electron separated from its atom. Fine, no problem. But what do we have? We have an atom, we have an electron. That's what the pictures show.
Yeah, that's
That's
done,
objectively.
done. Full stop right there. That says it all.
That's all we have there. Now, ionizing that left, I need two pictures.
I think with that, you finally put it to rest, at least in my mind. Because, if you take a picture of ionizing, all you have is an atom and an electron over there. Yeah.
Okay, the last one here.
You're the one that says the atom is missing an electron, but that's motion. You're adding motion.
I'm adding motion. I'm reading more than what's there.
You're saying an electron was removed here. You're already doing detective work. But no, all that's there is an atom.
A picture, you cannot synthesize a verb.
Oh, yeah, I think I got you.
Okay, and here's the last one. The fellow says, "Prove you understand the normal accepted theories." Saying I'm a dumb brain, huh?
Yeah, you're dumb.
Then teach the audience why you believe that those are wrong.
There's a lot of words there.
Yeah,
Prove, believe, and wrong.
Well, yeah, so I put prove, believe, and wrong. This fellow apparently comes from a monastery. That's probably where he did his schooling, whatever. He was part of the congregation.
I think that's all you actually do. All you do is explain the normal accepted theories.
Yeah,
but
to
the best of your ability. Yeah. Well, to the best of anyone's, you actually do a better job explaining mainstream physics than mainstream physicists.
Yeah, but see this fellow talks about proof, belief, and he says whether it's right or wrong.
Yeah.
This is what he's talking about. Oh, that has nothing to do with physics or science. It's got to do with religion. Where do you prove? Well, when you bring the good book, you convince the congregation, you say, oh, I have the evidence that the Lord has talked to me, or he's in communication with me when I'm in the bathroom or whatever, right? And so you show the book and you say, I have proof. And why? Because you're trying to make them believe. You're trying to show that everybody else is wrong except your religion or whatever, right? So yeah, we don't use proof, belief, or wrong, but you can see his language there. In science, we are only rational, okay? And what do? We do explanations, okay? And if you are not a scientist, otherwise you're not a scientist, right? And you are doing religion. If you talk about proof, belief, and what was the last one? And being wrong or right. What is wrong or right? An opinion, right? I mean, you're always wrong and I'm always right. So I guess my religion is better than yours, right?
Yeah, really, physics deals with hypotheticals in my mind. What science is all about is if this, then that.
Well, it's theories.
But that's what it boils down. Science, the shortest scientific what do you call it? Scientific method is if this, then that. You assume something, then you assume a relationship, and then you end up with a result. Then you look at that result and say, then comes the religion part. You say, is that really how it works? I don't think so. Let's try a different if this and that. And it's almost like with technology, where you kind of try a bunch of things until finally you find if that works, a then that works, and then a that you're satisfied with.
Yeah, and
that's
again,
how it works.
And again, everybody has a different satisfaction. This guy likes it. I mean, I can give you a theory,
Exactly.
a very simple thing that I always use. You find the window broken and the glass is on the floor. So you have three people who didn't see what happened. They come up with theories of how that happened. One guy said, well, the dog jumped through the window. Another guy said, no, Johnny was playing soccer or baseball and the ball went through the window. And another guy might say, no, your neighbor, he hates you, came in there with a crowbar and broke your window. Yeah. So these are different theories, okay? The assumptions, one is the dog, the other one's the ball, the other one's the crowbar. Those are the assumptions. But then the theory is based on those assumptions. And that's the way it should work in science or in physics, especially in physics.
But that's why I like the if this, then that. Because the if this is the assumptions, then is the hypothesis, that is the result, but also the result tells you how far off. There the belief part comes in. Because you could say an angel is what spins the earth. Right?
Yeah.
And a lot of people would be satisfied with that, but a lot of people wouldn't. But the satisfied part is the religion part, because you go, that doesn't sound right to me. It works as a hypothesis, until you dig, obviously, and I guess that's where the dissatisfaction comes in, where you go, that doesn't explain a lot. There's a lot here missing, so we have to work on something.
Well, this is the issue. The issue is, I always say that religion, especially like Christianity, is more believable, more acceptable than general relativity, for example. Because in Christianity, you can say, look, let us assume that God exists, right? So you put a guy there and you say, look, this bearded guy, that's my God. So you can at least present your object, your things. You say, this is God, okay? No problem there. We all understand that. We see a guy with a beard with a magic wand and say, okay, I understand what I'm seeing. I comprehend. You can't do that with general relativity. General relativity says we start with space-time. Okay, show me space-time. What are you going to put a concept there and say time is bent? Is that what your theory is? I mean, what are you going to put for space-time? So I can imagine God, right? I cannot imagine four-dimensional space-time. And that's when they say, well, you're not supposed to take it so literally, and that's philosophy. Well, they lose us. No. Show me space-time. Show me how it's warped, and then I'll understand your theory, let alone believe it. It's easier to believe in God, believe me. Okay, so we can...
My turn?
Yeah, no, well, your turn or anyone who wants to ask questions there. Yeah.
We got more everyone discussing among themselves, not real questions. I saw a few. Hold on, let me see if I can find it.
Yeah. Well, go ahead with yours first, then we'll give...
Well, you can answer these next time, too. But...
Well, if they want to answer at the end, put a question there at the end, start start asking
Well,
questions.
I saw
now.
some
Think
questions.
of good questions.
Well,
If they're not good, we're not going to answer them. We're not.
I saw some questions about time, but
Okay.
let me just go on to it.
Yeah, go with yours, and then we'll move on.
But let me start before I ask the question. Let me paint a picture, if you will.
Oh Jesus, I'm in trouble already.
Well, it starts with a question.
Okay.
Is there a such thing as time? But before you answer it, let me answer it.
Oh, you're gonna. Oh,
Yeah.
Okay, I'll show.
Time is a concept, so by definition, it does not exist. Easy. We won't use the term time, but we do understand that objects are in motion, and with our memory and intelligence, we can tell where objects have been and where they're gonna be. So
Okay.
far, so good?
So far, so good.
Just painting a picture, no
Yeah,
questions.
yeah.
So if we
You're
rewind...
not painting it, but you're painting a movie.
Okay, move. So if we rewind the matter in the universe ever further, here's
Okay.
the first question. Do we end up with the first frame of this movie? If you keep rewinding where matter was, do we
Yeah.
find a spot where it all came from?
Well, how can you do that? Because why isn't there a previous frame to that frame that you're looking for, to the next to the last frame? Isn't there a frame before that? Wasn't there a frame before that one, and so on?
So you're saying there's no first frame.
Yeah, you can't because the first frame would be the creation of matter, and
Yeah.
creation of matter would be nothing turning into something. With or without God, really, it doesn't matter, because whichever one you put in there, you have to tell us the mechanism. How did God create, something from nothing in His workshop?
Well, usually people just skip the mechanism part and they just say, "Well, that's the
No
part
kidding.
that I can't explain."
Yeah, no kidding.
And you're saying, isn't it much easier to just cut out the middleman and just matter was?
No, it's much easier, but it's much easier to think that matter more rational, really, to think that matter cannot be created from the void with or without God. You cannot turn something into nothing and nothing into something. And if you cannot turn nothing into something, matter has always been there, floating in nothing. That's much easier to understand than to say that something came from nothing. And that's why creationism in any form, Big Bang or whichever way they want to, sell it to you, don't work.
Okay, then I guess just to end this part of it,
Yeah.
if we use our intellect to fast forward this movie, do we ever end up with an end frame?
No, because we have another frame right after that.
So you're saying there's no beginning?
No, because the same thing. Now you're turning something into nothing. That would be the last frame. And how do you do that? I mean, how do you turn an atom into absolutely nothing? Even in quantum mechanics, they say you have the virtual particle. It comes in for a split second into the real world so swiftly that they cannot even measure it. They admit that because it goes back to where it came from. And so if when they talk like that, they're not making it disappear. It's not they're saying the particle came from nothing. In other words, manufactured itself and then demanufactured itself. No, they're just saying it came from space and went back into space. The particle is always there. It never disintegrates and turns into nothing. That's my point. So even under quantum mechanics, you don't have total disintegration, meaning conversion of atoms into nothing and nothing into something.
Well, just a quick, addition to all this is really the most hopeful part of the rope hypothesis that I think is the fact that if matter was always in motion and always will be in motion, and if we exist today, then it stands to reason that the drama of evolution, and also part of that being humanity, is an ever-repeating part of the universe.
Yeah.
So really, when you talk about the end of humanity, even really you're only talking about the end of humanity for
On
now.
Earth. On Earth.
And only for now.
Well, you can't even say for now, because maybe there's another planet somewhere in the universe with so many stars and galaxies. There's got to be planets there where life developed similar to the Earth, and there's a human somewhere out there also developed. Could be happening now in several parts of the universe. In fact, we may not be the only planet right now in the universe with humans. There's got to be maybe, who knows how many. But there's got to be life in other planets as well as humans, meaning our level of intelligence, which I say is the maximum that the universe can do. The most intelligent that Mother Nature can make a living entity is us. So if you don't think that, then you got to complain to your mama. You know?
No, I would take one step further. I think it wouldn't be living anymore by whatever weird definition you have of life, but AI, I think, would be the one step above that.
But AI is not. I don't know.
It's a weird form. I mean, depends on
that's
how you
a long story.
That's a long story. I won't get into that. But it also depends on how you define intelligence, etc.
Yeah.
But that really is, every time I think about the theories and all the pessimism around it, when you say we can't travel to another star, really the most hopeful part of it is that essentially humanity is immortal because it just keeps repeating.
Yeah, in the universe, humanity is immortal. I think life is immortal. That's in general terms.
Okay, so let's keep painting this picture.
Okay.
Under these assumptions, really is what they are.
Yeah.
What we could say that the matter in our universe, for just to keep it simple, the matter in our universe is almost like a bubble that's always just kind of moving around in space, which is nothing, right?
Right.
It's just ever moving, but this ever moving is also perpetual. There's no
motion.
I think we explained somewhere that since there's nowhere for this motion to go, not that motion is a physical object, but we kind of understand that just the fact.
It doesn't stop.
It doesn't stop. But because there's nowhere for it to be transmitted to. But still, that's bad language. But
it's like one atom can only move and force other atoms to move in the universe. Yeah. So they're all moving with respect to each other. That's
one atom can only move if another one moves it.
Right.
Which means every time there's always something
moving one atom to the other atom. So it's a chain reaction of where everything moves everything. That's all it is.
But then one thing that can be said is for every action there's a equal and opposite reaction. I guess that would be true because the motion is always there. It doesn't go anywhere.
Yeah.
So we have this bubble of incessant motion. So there's no motion lost. But then I guess there's no motion lost because there's no way for this bubble to stand still.
Oh, right.
It's not slowing down, and stopping.
Yeah.
It's not speeding up. It's not speeding up.
In fact, in my book, I have the situation where you have what I call the frozen universe, right? Everything is standing still. The only guy that's moving is God, right? But the problem with that is, and just think of God being in the 10th dimension. He's like not part of our universe, right? If you can imagine that. But everything's standing still. And all God has to do to create motion throughout the whole universe is move one atom from A to B. Soon as he moves it from A to B, all the other atoms change their distance, their location with respect to that atom.
Yeah, but
to move the universe, all you need is to move is one atom.
Yeah. Okay, side tangent. This is the hard question that I wanted to ask you as far as the rope hypothesis, right? Because that's really what I wanted to ask you about today. Because you talk, in my opinion, you talk way too much about mainstream physics and a bunch of theories that, we get it, they don't work. But you definitely don't talk enough about the rope hypothesis. And the reason I say that is because even under the rope hypothesis, there's a bunch of mysteries that we don't really get into the nitty-gritty about because the weight of mainstream physics today is just so much that it's so glaring that you never get around to talking about the rope.
A lot of people have trouble understanding the kindergarten stuff, so sometimes you can't even move beyond
also that. It's kind of hard to talk about.
Yeah.
But today I'd like to ask you some of those. One of them was one that a friend of mine came up with a while back when I told him about the rope hypothesis. That being, let me paint this picture. You got the sun. I'll put it in the camera. You got the sun, and the ropes are tied from the sun to my eye. That's why I can see the sun, right?
Right. All the atoms in the sun are connected to every atom in your eye.
So the rope twists and it blinds me if I look at it.
Yeah.
We don't care about the blinding.
Everyone torques. But every eye torques. Every rope torques.
Every rope torques.
Yeah.
The signal, I guess, starts at the sun. And then eventually makes its way to my eye, right? The torsion. The rope doesn't move back and forth like that, but it twists. It twists on this end, and over, at the speed of light, essentially, it gets to my eye.
Yeah, they say 8 minutes approximately.
But then if you put a wall between that, right?
Okay.
Now it gets complicated.
We have the sun, wall, my eye, okay?
I can no longer see the sun because of the wall.
Yeah.
I can no longer see the sun because of the wall, but the ropes from the sun to my eye are still attached.
Yeah.
And they're still torquing into my eye, so why can't I see the sun?
You mean why does the
light from the sun
why
not
does
reach
the
my
wall
eye?
block the?
Yeah.
Why can't I see the sun? Because there's at least one atom there on the other side in the sun connected to my eye directly.
There's a lot.
There's
of
a lot
atoms.
of
Yeah. There's
but-
as many ropes to
Yeah.
my eye as there are atoms in the sun.
Correct. And the issue there is that you
Hydrogen
have,
atoms.
let's go just one atom, okay, from the sun, just one atom, okay? We're going to look at this atom in the sun. It's connected to your eye right through the wall, right?
Yeah.
So it's not connected to the other atoms. It is connected to all other atoms, but there's one that goes directly to my eye through a whole bunch of atoms that form the wall.
We're just going to look at one to make it simple.
Right. So we're going to look at one atom, and that atom's connected directly to my eye. Okay, so there's a direct connection between that atom and the atom in my eye. And just one atom, right?
Yeah.
Okay, and it's going through all these atoms, right? The rope is going through all these atoms, this wall that's there, right?
But I remember at one point you said that, or you at least give this impression that atoms can't touch the rope.
Yeah, they can't. Yeah, they can't touch.
And that's what I would like to debunk today, because I have another example too.
Okay.
Let's keep it down for now.
Okay, so let's go with this one. So we have that atom from the sun. It's connected directly to my eye.
Yeah.
Okay, but what we have to understand is the following: that same atom is connected not only to every atom of the wall, it's connected to every atom of air that stands between the wall and the sun, and between the wall and my eye. So there's air.
Wall and the sun.
Yeah, there's air. There's air, and there's air
Okay.
on this side also of the wall to my eye, right? There's gazillions of atoms.
We could remove the air.
Yeah, but let's leave it in there for a second. We'll remove it. It doesn't matter. It doesn't change anything. My point here is there's, in fact, more atoms of air than there are atoms of wall. If we want to look at that, because you have all these atoms that extend from the wall all the way to where the air ends in our planet on the one hand, which is in between the sun and the wall, and then you have all the air from the wall to my eye, right?
Yeah.
So one atom in the sun is connected, all of them, to all the atoms of air, all the atoms on the wall, and all the atoms that are on this side of the wall, as well as the one in my eye.
Yeah.
But here we're talking about one atom in the sun connected directly to one atom in my eye, and one atom in the sun connected to gazillions of atoms, which are also connected to my eye. Okay, because I can see the entire wall in one shot. I don't need to look one atom at a time. I look at the whole wall. So that means all these atoms are connected, and we're talking about only one atom, right? Because that's the one that's connected to all the atoms, right? That atom, and that atom is connected to my eye. But look at how many rows I'm receiving, not only from that atom to all the atoms of air and of the wall, but all the atoms of the wall to my eye, and all the atoms of the air around there as well. They're all connected to my eye.
Go slow, go slow.
And we're trying to figure out one rope among gazillions of ropes.
Well, hold on. There's more atoms in the sun.
No, I'm talking right now. I'm just talking about one atom in the sun, so we understand what the problem is. The problem is that only one atom in the sun here that we're talking about, that one is connected directly to my eye without it being connected to other atoms in between.
Okay.
That's my point. Okay.
Yeah.
So that one's connected directly to my eye.
Yeah.
But that atom is also connected to gazillions of atoms of the air, of the wall, and of the air, and of that come to one atom of my eye.
Okay.
So that same atom of my eye is connected to a bunch of atoms, and that atom of the sun is connected to a bunch of atoms.
Yeah.
And I'm not talking about just a bunch. I'm talking about gazillions of atoms, and we're just trying to isolate just one that's connected directly to my eye.
Yeah.
Right? And so you can imagine what's happening here.
No.
Maybe that one, that signal is coming directly to me. It's not interrupted at all, but it doesn't matter because I'm not going to be able to see that one atom because I'm being blinded, you could say, by the gazillions of ropes that are coming to my eye. What I'm going to see is the whole picture. I'm not going to see that little one atom that's just shining right through all the others. I'm going to see the whole wall. If I could see the air, I would see the air, right? That's what I would see. And you're trying to isolate one atom out of gazillions of atoms, say, oh, that one that's connected to my eye, is that interfered or something happened? No, what it is, it's just overwhelmed by all the other atoms that are connected to my eye. And I'll give you the scenario. Look at this. Let's say you make a little peephole in the wall.
Yeah.
Okay, so we make the wall, say, is, I don't know, a couple inches thick, right?
Yeah.
I make a little peephole and I can see there. am I seeing, and we don't have to see the sun, it could be a tree, right? So I see a tree through the little peephole, right? Am I seeing the tree directly? The answer is no. I never see the tree directly. What I see is the relay of all the atoms that are in between, which are all the atoms of the air.
Yeah.
And so the tree, that one atom of the tree, just one atom of the tree, is connected to all those atoms of the air. And all those are relaying the signal through the little peephole to my eye. There's gazillions of atoms in the hole that you made in the wall, let alone all the air that's between the hole and my eye. So you have gazillions of atoms, and we're going to isolate one atom of the tree connected directly to my eye through all these atoms. So I'm not seeing the tree directly. I'm seeing the relaying of gazillions of atoms, and only one is connected to me, which is not relaying.
So let me see if I got this right. So you're saying most of what we call vision, or even beyond vision, because really detection, if you use a machine, you're saying even a machine wouldn't be able to detect sun rays from the sun through a wall, because really what it does, I mean, it's so minimal what gets transferred directly. Really, when you get a sunburn, it's not really the sun directly. The ropes are directly from the sun to your skin.
It's refracted.
That's a very minimal amount compared to I don't know, fraction. I don't know. It would have to be some. Let me finish. It would be some infinitesimally small compared to the relaying of.
Right. Relay by far beats the one that's directly connected to your eye.
I think that's what it is.
In fact, let me give you a scenario. We have glass, right? And you see the sun coming through the glass and getting to the plant in your flower pot, right?
Yeah.
And you're saying, okay, the standard explanation is all the atoms go through the glass. It allows the atoms to go through, and it's a hit or miss according to these people.
Oh, forget these people. We're not talking about these people. No. We're not talking about these people.
Because I'm going to make a comparison.
So we don't need the comparison. Just once. Do it without the comparison.
We need it. We need it so that people see the difference. People think that the photons, the little balls, are getting through the glass, and I'm saying it doesn't get through nothing gets through the glass. Okay, what you have is the atom in the sun going through all the atoms of air until it gets to the glass. There's a relay of the signals, and then when it gets to the glass, that atom, since it has a structure that allows for the vibration to pass to another atom, to another atom, to another atom until it gets through the entire glass, and then from there to your eye. So it's all relay. There's only that one atom is connected to all these other atoms that are relaying, and only one of those ropes is connected directly to one of the atoms of my eye.
No. Something's wrong here. Because if I'm in space, no atoms in between, I can still see the sun. No relay.
There are atoms.
No.
What do you mean? If I went in space?
In space.
Yeah.
No atoms for relaying.
Uh-huh.
I still see the sun.
Yeah.
You're saying I wouldn't see the sun because there's no atoms to relay.
No, you see this. No, because then you have more direct sunlight than relayed.
But that's all you have. You're saying
no. First of all, let's make sure we understand. There's 10 to the minus 11, 10 to the minus 12 torr in outer space. Yeah. That doesn't mean it's completely empty. It means there's a lot of garbage there, but it's not the amount of garbage that we have here on Earth with air and so on.
Basically nothing.
There's a lot of them.
Wait, so you're saying
thousands?
Hold on. You're saying if you remove all the matter, theoretically, right? If
Okay.
you remove all it, we're blind?
No, the contrary. You have no relaying. You have more direct light.
But we'd be blind.
Well, yeah, I mean, let's assume you put a machine there or whatever.
What do you mean machine?
Well, to detect whatever you want to
Why?
detect. Well, all I'm saying is
if you put
a detector. Okay, you put
a person there, but that person would not see the sun, is what you're saying.
You're seeing the sun because there's no relay. It's just direct sunlight, direct light.
But you're saying most of our vision comes from the relay.
Almost all of it. Almost all light is relayed.
But then if you remove any relaying, you would not see anything.
If you remove all the relaying, you would see because you see it it would be connected directly to your eye. If you didn't get blind, it's connected directly.
So
from the sun directly to your eye.
So since there's nothing else to distract your eye, I guess you would see it.
That's my point. You're not overwhelmed by all the other garbage, air, and whatever you have there that interferes. But otherwise, you have no relay, and that means you see it directly. That's my experiment for showing that quantum is nonsense, because you just do the slit experiment in a vacuum. Very simple. So you do it first with normal air, right? And then you pump down the system while you have the fringes there. And what you should see is a lower intensity, because you have less atoms to relay the signal. Okay?
So if you had a wall in space,
yeah, you have a wall.
You'd still see more of the wall, I guess.
You would see only
more to distract.
Right.
Is it a distraction
But if you
issue?
remove that, if you can remove all
that's
the
weird.
air of
Hold on.
solar wind, let's say you remove the entire solar wind.
Hold on.
Yeah.
You're saying that's a weird juxtaposition, because it's a proportional issue. That's what you're saying. So you're saying, since if you remove everything there,
Yeah.
you would see the sun, but only because that's all there is. And if you put a wall, most of your vision is blocked by the wall than the sun.
And they relay a lot of stuff there, and you're trying to see one. Just to say, you're trying to see the signal coming through one rope compared to signal coming from a gazillions of ropes that are coming to that same atom. There's no way you can detect that single signal.
That's a very weird one.
Yeah. Something to think about, at least. And again, that's one theory. Someone might come up with a different theory. See if someone has a question.
How do we test the rope hypothesis?
You don't test it.
We do test it. We test it every day with dropping a pen.
Yeah. You can't test, because testing means hands and eye. That's what testing means. Experiment, right? And if you run an experiment, you can't detect that which is invisible and intangible. An object is not that which is tangible or visible. An object is that which has shape. It can have shape and not be tangible or visible. And so you cannot detect, with any experiment, you cannot detect the mediator of gravity, the mediator of light. You cannot detect electricity. I mean, that's why you have to theorize. You have no other choice but to visualize and theorize and tell the world how you think all these things work. That's it. You can't test these things. That's why science, we don't test anything. Because testing means that you're going to try to get evidence to convince the crowd. You're just interested in proof, in evidence, in convincing people to believe like you do. And we don't do that in science. In science, all we do is explain rationally the mechanism. People can believe then whatever they want.
You've talked before about one-way touching. Explain that real quick.
What was the context?
I think that the context was magnetism, but I'm not sure. Because with magnetism, I don't have to explain it, but essentially it's a bunch of threads going like this.
Yeah.
And the threads touch the stuff, but since they're threads, they don't get touched by the matter. I don't know if that was the context.
I'm trying to remember the context now of that, but no, it doesn't come to mind. But I know what you're talking.
Yeah.
I'll have to take a rain check on that one.
But
there's a one-way touching. You can touch the ghost, but the ghost can't touch you, so to speak.
Yeah,
That's more or less the context. But I can't remember
what the context was. I think it was magnetism, but I'm not sure. The problem I had with the one-way touching, just as
okay. I guess it could be that the fact that, when you try to touch the mediator of magnetism, like you get your hand close to the magnet, there's a field going on in there, which is all the threads going around under the rope model. You can't touch those ropes. They're going right through you. Okay, but as soon as you put something in there, like a metal or whatever, that guy can touch it. Yeah. So it's like, in that sense, that's one context.
But I don't know if that's that's not really one-way touching, because that only gets moved because the metal is aligned in such a way that it gets pulled by these.
I'm trying to remember the concept. It doesn't come to mind.
I was hoping you would remember.
No, I'm too old. I'll have to take a rain check on that one. One-way touching. Yeah.
What else we got? Well, does quantum mechanics explain anything?
Well, quantum mechanics is not in the business of explaining. All of mathematical physics is not in the business of explaining. They're in the business of describing. They describe mathematically what they can see, what they can measure, and you can only measure what you can see, and that means that you can measure maybe weight. You can meaning an object, how it pushes down the scale. You can measure that. You can measure how far something went in how much time. It's measurements, because they're going to do calculations and make predictions on where an object can be if it runs so fast and so on. But what they don't know is what they're looking at. And here, I've got a scenario here that might be interesting to put up here. This is an object that's moving, okay? And you cannot see what's moving it. And so you ask the question, well, how come this is moving? You know, what's pushing it, okay? And so one guy says, oh, I know, I can tell you, here's my theory. And he measures how fast that thing is moving and says, what's happening is all these particles are pushing the thing, okay? It's, these particles coming from the left. And, you might have a million questions, why don't they come from the right or from above? But right now, this is the explanation. The guy says all the particles are pushing this thing to the right, okay? And he does his calculations, he does his measurement, he does his equations, and so he says, okay, I've proven what? That particles exist? No, you've only proven how fast that thing goes. You can predict how far it will go based on, on your experience, because you measure this a million times. You say, I can predict now where it's going to go, right? But you cannot predict. You cannot explain, you cannot come up with what is pushing that thing. You are inventing, you're saying, well, what's pushing it is all these particles, but that's your theory. And maybe your theory is completely wrong and it's worthless to do your math because you're using the wrong hypothesis. Let's change the hypothesis now and let's say there's a different explanation. Here's the explanation, okay? And what you have is this thing is torquing and moving along a screw, okay? And so this is a different mechanism for the one that you had, which was the particles pushing the thing, okay? This is simply something twirling around some axis, right? That has all these these threads, and so that's what's causing the movement of this thing. And so you have a different mechanism. This mechanism is not the same one as this one. These two are different mechanisms. So you can have the same equation for the same movement of something in a certain direction. And that's the problem we have with all these invisible things that we have out there. We don't know what's causing them. All we can do is speculate and give a hypothesis, an assumption. And based on that assumption, you say, okay, what if, right? What if light is mediated by a rope, or DNA like two-strand rope, etc., right? And that's a what if. And you can say, well, what if it's particles? Okay, you can make all those what ifs, and then you find out which one can work with all your explanations. If you can say, well, I can explain gravity here, I can explain electricity here, magnetism, then you have a pretty good idea. That's probably, if it walks like a duck and poops like a duck, then probably it is a duck, But if you have the particles and someone said, well, how about the particles coming from the other side? Well, I don't know about that. Or, he can explain pull with the particles, right? And then that's when you have to get rid of that assumption. You say, well, that assumption is probably not as good as the other one. In other words, then you apply, what's this guy?
Occam's razor?
Yeah.
Occam's razor.
Occam's razor. That's what you apply.
The
least assumptions.
The one with the least
complicated
magic, I guess you'd say.
Yeah.
Because,
the least ad hocs that you can put in there. So that's the only, and again, that comes down to belief also. You can choose whichever one you want. Again, in science, we don't believe, we just explain objectively so you understand the mechanism. Once that is done, what comes out of the screen is objective. What everybody understands is something else. That's subjective. But what comes out of the screen is the same for all of us. So once you explain the mechanism, that's what comes out of the screen. Everybody then can believe or...
Well, that's a good segue into the next question. I like this question. How do we know the difference between an examination and a narrative?
Examination?
I think what we're saying is what we see and what we infer from what we see. Because you could see something happen... And you can have a story for something that happened, and it might not be like. How do you tell the difference between something?
Well, this is the issue. What comes out of the screen, what comes out of a book or whatever, that's objective. Now, what the person who reads or the person who watches, the observer, he's subjective, and so he might understand something different from what's coming out of the screen than the guy next to him.
I guess that comes down to the bird. the picture of a flying bird, you see a bird,
Right.
but you can infer more things from the
Right,
picture,
right.
something like that.
And we read more into it than what is there.
Well, no, but that is kind of our job as physicists. Also, when you see the pen fall, and you want to explain the invisible, you have to infer things that you didn't see.
Yeah.
In a weird way.
You do infer, but this is the point. The point is now you make your own movie.
Yeah.
Because you're going to talk to the crowd. You're going to explain a mechanism to them. So you make your own movie. And you say, this is what I inferred from experience, experiments, whatever. It doesn't matter what you did. Maybe you had a bad dream. But the point is now you put your picture on your movie, right? And the movie, what's coming out of the movie is objective. The images coming out of there are the same for everyone. Mm. Everybody interprets something different, and so this guy says, "Well, I think I have this theory." The other guy has another theory or a different understanding. But what comes out of the movie is the same for all of us. That's objective, and that's what we talk about in science or physics, right? Physics means that you make a movie. What comes out of the movie, the explanation, the mechanism, should be the same for everybody because that's what's coming out of the screen. But what people interpret, what the audience interprets, and what each one believes is something totally different. That's subjective.
Is there a difference between the words explanation and narrative?
Yeah, because narrative does not... Narrative is just like usually chronological narrative, right? It's just
it's a sequence
what
of
happened.
events.
Yeah, what happened. But there's no interpretation there, which is where the explanation differs. The explanation is
puts a fine point on answering a question, whereas a narrative just
tells you what happened. This is what happened.
It doesn't even tell you what happened. It's just a sequence of events. It might not even have happened.
You can even say that's almost what comes out of the screen as a narrative, but there is an explanation because you have to show some kind of mechanism
let
with
me
the
answer
explanation, whereas narrative does not really give you a mechanism, something that you cannot see.
I got you.
Yeah.
In Aesop's fable, the story is a narrative, but the explanation is the moral of the story. They never explicitly say the moral of the story. Yeah. They never say, don't do this anywhere in the story.
They just tell you what it is.
No, they don't. They never tell you the moral of the story.
It's like...
it's inferred. That's the explanation.
I think there is a moral to each one.
Yeah, but it never says it in the fable. It never actually says... And that's why you should...
I read a million of them. Now you got me. I have to do my research.
What I mean is, if someone tells you the hare and the tortoise, nowhere in the story do they say, and that's why you should take your time with things. That's never part of the story. That doesn't make sense.
I think there is...
no. That's for everyone... Because you just tell the story.
I got to look at that.
What I mean is...
I thought there was
whether it is or not, you could tell the story without saying it explicitly.
Well, that's true.
And the explanation part... Basically, you could say the explanation even without the narrative, because you could just say, "Hey, this is the moral of the story."
And not only that, people can infer their own moral. Right, that's true.
I have a side question.
Okay.
Is there a gravitational center to the universe? As in, we have all the matter in the universe, and if we calculated, like calculation, if we calculated the average or the center spot of it, would there be any more weight there? All the ropes pulling towards it, is it canceled? Is there no gravity in the center of the universe because it's all being pulled apart? Well, you're in the very center of it.
Okay, but there's two universes we can imagine. One is a ball, right?
Okay.
In which there are galaxies on the inside of the ball.
Yeah.
And the other one, which is the same notion as space-time, if we come to think of it. And the other one's where all the galaxies are on the surface. No, are on the surface.
Neither, I thought.
Well, no,
I thought a third
we can imagine. Okay, we can imagine. We can imagine several ones.
Okay, let me tell you the exact one I'm thinking.
Okay.
Galaxy, the shape of a galaxy, a flat spiral.
Yeah. Okay.
At least the common galaxy.
Yeah.
Let's imagine the whole universe as a flat spiral.
Okay. Which is one universe.
Yeah, let's take that one.
Yeah.
Because that's the one I can kind of see.
Yeah, then you can imagine everything pointing towards the center, I would think, because that's what gravity is. If everything's connected, everybody would tend to go towards the center.
But does that mean that if you were in the very center of... it's kind of like the question if you're in the center of Earth. If you're in the center of Earth, do you feel any gravity? I think the question is no.
If the thing is rotating, if the whole thing is rotating, then you have the outward push against the inward pull, and you have no gravity. You have maybe a tie,
Yeah.
or something along
But I
those
think the
lines.
same thing applies to the universe itself. If you're in the center of the universe, you also wouldn't have any pull. It'd be like a gravitational no man's land.
If it is a center, the issue is, again, if we had God's point of view, if we could stay outside the universe and look at the whole matter in the universe, we'd say, oh, we can see what the shape of it is. And then we could do all our calculations, say, okay, it's a sphere, or it's just a surface of a sphere, or it's flat, if we could see that. But unfortunately, we don't know what the universe, all the matter in the universe looks like, what kind of shape it has.
If you had to bet, what do you think the shape of the matter of the universe looks like?
I think the way we have to do it is we have to hypothesize. We make assumptions for each one of those shapes.
But you never did?
No, I never did that, but no. The reason is that it would be up to mathematicians to say that is a job for mathematicians, where they would go in there and say, look, let's assume it's a flat disk, and then what would be the consequence, and what would be observed if it were like that? And they have one hypothesis there, and then they go to another one, make another assumption. They say, what if it's a sphere with all the galaxies, within it as well? And that would give you a different result. And if it's just on a surface, that would give you still a different.
Why would you need mathematics for that? If you
No, it's just to show you in this sense. If the galaxies are not coming towards each other, then it means the whole thing must be spinning, pushing everything out at the same time that gravity is pulling them in.
Yeah.
And then everything more or less would stay where they're at.
Yeah.
In general terms.
But that applies to any shape, I guess, except, in my mind, that always tends to be the same thing as a galaxy. I can't imagine.
More or less. It would be like the stars in a galaxy. But remember, then you have the magnetic field of the universe, of all the galaxies in the universe, just swirling around. And how does that affect the coming together and the going apart of galaxies?
I'm guessing
so you have a lot of stuff in there.
Magnetism doesn't have any centrifugal force, does it? It's spinning, but it doesn't have any centrifugal force?
No, only on the thread that's spinning. But the point here is that it's not like the thread is flying away, because it's tied already to all the atoms that are doing the spinning. So what you have is all these threads, all these magnetic fields, not only of the galaxy, but of the entire universe. The entire universe has to have a magnetic field. How does that play into gravity? Does it keep things apart by, having threads moving in opposite directions and pushing them apart against the pull of gravity? You would have to have God's eyes for all that. We only have a small portion of the universe where we can see stars and galaxies, and you're trying to figure out, what the universe looks like, or the matter, how it's distributed. You can only hypothesize and say, what if? That's all you can do.
How to buy your book, Bill?
Well, you pay money and you buy it.
How do we know if someone understands something? Ooh, there's a good question.
Well, again, the issue, the understanding is the following.
That's a tough one. How do we know if when someone understands something, or if someone understands something?
No, but this is.
I guess to answer that, let me answer real quick.
Yeah.
If they can tell it back to you.
Right, in your own words, that's one issue. But what I say always is, what comes out of the screen is objective. One talks in the background and tries to explain what you're observing. That helps a lot. But if after all that you still have a different interpretation, well, all you got to do is ask questions, and we clarify each point by point. But what we're interested here, at least, is that you understand what we're proposing. Well, we're not trying to convince anyone. You can believe whatever you want. You can even trash it and say, I'll go back to quantum or whatever. No problem. Everybody can believe in whatever they want. My point here is we try to explain the theory so that you understand how we think the universe works. It doesn't mean that is the way the universe works. It's just one way that we're proposing. It's just an explanation. It's what we call science, physics. Explaining how we think it works.
Is the rope theory a unified theory? I don't know what that means exactly.
It is a unified. If we're going to talk, I guess you're talking about grand unified theory.
What connects the micro and the macro?
Yeah, that's one aspect, but the real aspect is what connects gravity to light, electromagnetism. And in that sense it is, because we're using the same mediator That's something that quantum and general relativity cannot agree upon, because quantum works with particles and forces, and general relativity works with space-time and this continuous field, whatever that is. It's a concept. And so these two don't really match. And so what they're doing in quantum, they're talking more about quantum field theory. Why? Because they like the word field. And how does that translate into general relativity? Well, they say a particle is the local vibration of a field. And so now we have this local vibration of a field which extends all the way to the other side of the universe. And that continuity allows them to weigh something on space-time, bend it, and create gravity. That's what string theory is trying to do, at least from a qualitative standpoint, right? But it won't work, because again, you cannot reconcile a discrete particle with a particle that extends, right? Like a field extends, like a cobweb extends. In this case, a three-dimensional spider web, right? And you cannot reconcile one with the other. And they don't use the spider web anyways in quantum mechanics, all discrete particles. It's only to try to reconcile it with general relativity where they put the field and they say, oh, the particle is really a local vibration of the field, but the field extends. Only because they want to reconcile it with general relativity. But that's not how quantum works. Quantum works with discrete particles. That's how it's explained. That's how it's described mathematically. So there is no reconciliation, and that's why they have to invent string theory, because they're trying to show that this little string, which is a vibration of a closed loop string, is not only locally vibrating and creating the particle, but it can link up with chain link kind of thing and extend throughout the universe. And that's what they're trying to do. They're trying to invent the mathematics for that. But the qualitative part is already dead. There's no way you can reconcile it.
Do you think that they do a better, I don't want to say do a better job, but do you think their mathematics would align better if they had the toroidal helix in mind? During light calculations, during gravity calculations, do you think it would help them at all? Instead of trying to calculate everything with particles or waves, I don't know if they even factor that into the mathematics, but do you think it would help if they, assuming you had someone who did all the math on light and phys and gravity, do you think it would help them in their studies of mathematics of the universe? Do you think it would help them to have the rope hypothesis in mind?
Well, the first thing we need to understand is that torsion has been so thoroughly mathematized. The math is already out there.
But do you
all you would need to do is say, instead of particles traveling in a straight line
at x speed,
now you're talking about torsion. You're talking about a signal or propagating along the rope. Okay, so that's the first thing. The math is already there. But if you have a different, again, like I showed a minute ago, either you push this thingy, with particles, or it's moving. It's like it's screwing into something. That's a different mechanism. And so if you know that it's a screw type of mechanism instead of a particle pushing mechanism, now you have a different, not mathematics, because the mathematics is really for the visible stuff.
Well, yeah,
but you have a different mechanism.
That's the thing. That you think if they took the rope hypothesis as a qualitative conceptual basis of how the details of the universe, or the basis. I guess I don't know how else to say that.
Foundation.
As a foundation. Do you think that would help the mathematics in any way, or change it in any way?
The mathematics may not change. I doubt that the mathematics will change. For example, I do Schrodinger's equation with my model, so I don't need to change the mathematics. Schrodinger's equation works perfectly well. In fact, it works better with the rope model of the atom than with a planetary model. And even Bohr's equation, where he created this notion of the planetary atom, works much better with the shell model, which is the one chemistry uses anyway. They use the shell model. Why do they call it shell? Because they've turned the orbital into a shell, into an energy level, whatever that is.
Do you explain sound, the phenomenon of sound, or the concept that we call sound? Do you explain its effects the same way that mainstream physics does?
Yeah, we have no difference with sound. Sound is it's just vibration of molecules, rarefaction, and
So at that level,
compression.
it's kind of the same because you're still using balls as atoms.
Yeah. We have no difference with sound.
Someone says, yes, I think it is a unified theory, the most awesome one.
Yeah, it is. It's a unified theory because we use a single medium to explain gravity and to explain light. And quantum and general relativity have not agreed upon, the mediator that they're going to use. One uses particles, forces, and the other guy uses fields, really, because even though quantum gives lip service to the field, it doesn't use the field. Okay, they call them quantum field theory, but the field is put in there just to match it with general relativity. On the other hand, general relativity talks about extended mediators such as field and space-time, which are supposed to cover the entire universe, right? And so now they treat it as a sheet only for the purposes of giving you a physical interpretation. When you say, well, what is a sheet? Well, it's four-dimensional. You cannot imagine it. And it's a field, and that's a concept. It vibrates, a concept that vibrates. And we put a ball on top, it bends it, and you say, well, is that true? I mean, we don't understand it either, but don't ask that question. That's what it's done.
Is the rope hypothesis gaining any ground in the scientific community?
Well, it doesn't. It's for the handful of people who manage to come through our channel and get acquainted with it. And again, we're not here to convince or create a religion.
Though, because
yeah.
Imagine you hear one thing your whole life, and it's really the people who still have that like nail in their foot of physics, where it's like it doesn't scratch that itch of logic. Like it still didn't. Particles don't do it. Waves don't do it. We all kind of brush over it.
Yeah.
We use all these like net that. Space-time gets bent down, and that's why the thing goes down. Why does it go down if we're using gravity to explain gravity kind of thing? All these things kind of still stick in the head of rational physicists who are doing all this, like, they're doing math, obviously, but they still want to know what's actually happening in it, and that itch was never scratched by these, like, half-assed qualitative explanations.
One other thing I say is that if mathematicians, if they just stuck to math, no problem. They're in their world, in their own field. But the problem is their math is worthless if they cannot use that math to explain causes, mechanisms of our real world. And they give you these irrational explanations like, bending of time is gravity. And you say, but that's irrational. And what they say is, we don't understand it either. But we don't care about that. But if you don't care about it, if it's not in your job description of
why bother with it?
Why have you crossed the line into philosophy, as they call it, right? Semantic. Why are you crossing the line and trying to give me a physical interpretation? If it's not part of your job description. And the answer is very simple. If they don't cross the line, their math is totally worthless.
Yeah.
They have to give you a
it's not worthless, but no one's interested.
No, but it's not that. It's that it's worthless for physics.
Oh, yeah.
It might be useful maybe to develop technology. You can say, oh, but I measured here, and this is what I got, how much force I got. I can use that somewhere. In that sense, it could be useful for technology. But where it has no purpose or role is in explanations, which is what physics is about, which is what they call philosophy, a natural philosophy they used to call it. That's what physics is. Physics is, tell me how this universe works. Yeah. I want to know how gravity works. I want to know why this pen, falls through a floor.
Well, it's more, I would like to be able to visualize it accurately. I want to be able to visualize the details.
Not accurate, rationally.
Oh, yeah,
that
rationally.
You can understand it. That you can make a mechanism, people look at it and say, okay, I understand what you're proposing. Doesn't mean you're going to believe it, just means I understand what you're proposing. But you cannot understand what these people are proposing because they're saying it's the bending of time. What do you mean the bending of time? How do you bend time? Yeah. Well, we don't understand it either. Why the hell are you giving me that stupid explanation,
Okay, we're an hour 40 in, so I'll ask the last question, which is something like, there's someone who can't find your book.
Can't find my book?
Buy it.
You'll see it there in the, my site, ropehypothesis.com. ropehypothesis.com. There's a section called books. You'll see all the books there.
Oh, we got one more question.
Yeah.
How was your math?
My math's great. Math like mathematics. Or
Yeah, your math.
yeah, I've got a minor in math, but
Not a major.
I don't like to say it because people say, "Oh, you're a mathematician, Bill." Yeah, I was very good in math, but it has no, we use it in engineering as well. I was an engineer for several years. But the point here is that math has nothing to do with physics. That's the point.
That wasn't the question. How bad are you at math? That was the question.
I'm very good in. I think I'm pretty good in math. Many calculus courses and so on.
You beat my tough question, but you did good. I'm proud.
But I love math. I really like math, but math has nothing to do with physics.
I tried to get it with the sun wall question.
Not with the question I'm trying to answer. I'm trying to answer how does gravity work. That's what I want to. I don't need any math for that.
Well, maybe you can help someone with it offline.
Yeah.
Write them directly.
Yeah. Okay, folks.
That was fun.
Well, we'll see you maybe next week if we're still alive, right? We'll see you then.
Bye, guys.
Bye-bye.